Greetings, everyone. Welcome to the ION webinar featuring the paper Multi-Slices Navigation Approach for Unknown 3D Environments Using Micro Aerial Vehicles. This was published in the spring 2021 issue of Navigation. Today's webinar will be presented by Dr. Haytham Mohammed, one of the paper's authors. Dr. Mohammed is an R&D researcher at Aviation Research Center of the Arab Organization for Industrialization. He is a lecturer at the Arab Academy for Science, Technology, and Maritime Transport. He received a PhD in geomatics engineering, electrical and computer engineering from the University of Calgary in Canada. His research interests include unmanned aerial systems, navigation, robotics, laser scanning, sensor integration, remote sensing, and mobile mapping systems, and embedded systems. We remind you this paper is available to download from our website free of charge, and the slides and video of today's webinar will also be posted to our website tomorrow. We greatly appreciate the time and work that Dr. Mohammed has put into this webinar. During the presentation, if you have questions, you can click on the Q&A button and type your question in. We will address the questions at the end of the presentation. So thank you for being here, and now we'll turn the time over to Haytham.
Okay, thank you very much, Ray, for the introduction. Hello, everyone. I'm going today to present a paper entitled Multi-Slices Navigation Approach for Unknown 3D Environments Using Micro Aerial Vehicles. The small size of the maps, they are well suited for various applications, for indoor application, and especially search and rescue operations. Moreover, they have become active members in most of these operations. This slide shows some indoor applications such as firefighting, tunnel landslide, floods, earthquake, tunnel inspection, police services, and finally, logistics. In order to navigate a map inside indoor environments, it requires an accurate vehicle's navigation parameters, such as position, velocity, and orientation. But unfortunately, the GPS signals are blocked inside indoor environments. Furthermore, the situation is getting more difficult when the environments are unknown, which is typically the case in most search and rescue operations. Thus, the vehicle has to build a map for the environment and simultaneously localize itself inside this map. SLAM is a basic approach that addresses this problem. Various approaches provide solutions for 3D representation. However, these approaches require expensive embedded systems to afford high processing memory and computational costs. Because of its exposure to risks in search and rescue operations, the map should be equipped with a low-cost navigation system, which is insufficient for high memory and computational load. The principal aim of real-time map construction in the search and rescue operations is to facilitate the navigation task, and that's it. So constructing a massive 3D map is not required in such operations. Hence, it should have been a way for constructing the map with low memory and computational costs. This slide shows some examples for different 3D map representation methods. For example, voxel occupancy grid, and standard point cloud, and finally, elevation map. This paper proposes an efficient real-time 3D SLAM method using multiple 2D point cloud slices or maps. This method depends on low-cost sensors to fit the tough situations of the search and rescue operations. The main idea here of the proposed method is to divide the entire map into several 2D maps or slices based on the height of the map, as shown in the figure. This is map number 1, map number 2, and map number 3 for the whole environment or the entire environment. This means each map has its own height and it covers part of the environment, as well as a transit region between each two successive maps to enable connecting neighboring maps. Like here, it's a transit region between map number 1 and map number 2. And also here, there is another transit state between map number 2 and map number 3. This splitting process aims at reducing the memory consumption and processing costs of the entire constructed map, and also avoiding restrictions for assigning grid size before the flight like other methods. Moreover, for more memory reduction, the proposed method retains the executed trajectory for backward return, instead of building another 2D map slices during the exit process. The proposed method is divided into 2 phases. These phases are continuously repeated until the mission is finished. Phase number 1, the 2D point cloud of the laser scanner rangefinder is leveled using the inertial sensor in order to mitigate the impact of the vehicle's rotations on the scan matching process, as the map is able to translate and rotate around all its axes, 6 degrees of freedom, as shown in the figure. The vehicle here can make a yaw and pitch and roll, okay? Thereafter, in phase number 2, it contains the process of building the maps or slices of the entire environment, as well as the transit region between each 2 successive maps. This slide shows phase number 1, which is the roll and pitch compensation. Here, the roll and pitch angles of the map are calculated from the accelerometer measurements, as shown in the upper figure, okay? These angles are used to calculate the rotation matrix, which is R level, okay? And consequently, level the current scan in the body frame, as shown here in the figure. Here, the blue rectangle is before leveling, and the red one is after leveling using the roll and pitch angles. The current leveled scan in the body frame, together with the previous leveled scan in the mapping frame, are fed to the improved reference keyframe, IRKF algorithm, to perform the scan matching process. The IRKF algorithm estimates position and heading, which is denoted by PX and PY and theta of the map in the M frame, which is the mapping frame. And here is the rotation matrix, okay, and is computed from the roll and pitch. This slide shows phase number 2 for building the maps. The onboard system is divided into 2 subsystems, namely autopilot subsystem here on the left and navigation subsystem. The autopilot subsystem provides the roll and pitch angles to the IRKF algorithm. The navigation subsystem provides the 2D point cloud and the vehicle's velocities, and finally, the height of the vehicle. The IRKF algorithm builds the map with maintaining the same height. This is called map building state, which is here, map building state. As long as the vehicle can find new gaps or new area, it's still building the current map, and it doesn't perform a new one. When there are no gaps are found and the vehicle has visited all the available gaps in this height, the map building state is stopped, and then the transit state begins. here. The map building state will stop and then go forward to the transit state when there is no gaps and no visited and no new gaps or new areas. In the transit state, the vehicle fly downward or upward in order to find a new gap. During the transit state, the transformation matrix is estimated for connecting the neighboring maps in order to connect map number 1 with map number 2 and map number 2 with map number 3 and so on. If a gap is detected, the vehicle returns to the map to build the next map and so on until finish the mission, or until there is no gaps, then the vehicle will return back and using the same trajectory as I told you before. In order to achieve the proposed method, a customized hardware is implemented as shown in this slide. Here is the utilized MAV in the upper picture, and here is the laser scanner rangefinder and the optical flow and laser rangefinder in order to detect the height from the surface, and Navio 2 and Raspberry Pi, which is the autopilot for the MAV. Here, this mini PC is for gathering the point cloud that is formed by the laser scan rangefinder, and also all the computation for the point cloud is done here, and the map is saved here. The scan matching result of the transit state is studied using different algorithms in order to choose or select which one is better in order to perform the transformation matrix for the neighboring maps, such as iterative closest point and corner registration, and also IRKF algorithm. All of these are studied. And finally, we found that the IRKF is the best. And here in this slide, figure A shows the raw point cloud for an example room. And figure number B, it's the corner registration method. And here, when we merge the raw point cloud with the result when we're using the corner registration method. And here for D, it's the IRKF algorithm. And the last figure, which is E, when we merge the raw point cloud with the results from the IRKF algorithm. And it is clear that the IRKF algorithm gives much good results than the others. Here, it's one of the experiments. Actually, we made real data, okay? And here in the upper figure, it's the entire environment. And it is clear that there is 2 maps are built. Here, map number 1, which is the green points. And for the black dots and this arrow shows the transit region between map number 1 and map number 2. And for the red dots in the middle, it's for the trajectory for the MAV. We started here, and the MAV moves along this corridor until reach the end. In the lower figure, or in the bottom figure, it's a 3D view for the environment. And it is clear that there is a height difference between map number 1 and map number 2. And also it is clear that we didn't use much memory because we used only some points for representing map number 1 and as well for map number 2. And if there is another maps, we will use a very low memory because we just store the coordinates of just a point instead of the voxel or even another methods. Here in the upper figures, it's a real pictures for the environment. And in the lower right figure represents the takeoff region. And here for the map number 1, and this region for the transit state. And it is clear that the map decrease the altitude or the height in order to find a new gap. And after reaching or getting a new gap, it starts to build a new map, which is map number 2. And after finishing map number 2, it starts to land. This slide shows another experimental results for a different location. And it is clear that here it's map number 1, which is in the green dot. And here we start the map. It is clear that when the map didn't find a gap or a new area can move forward, it stops building the map, and it starts the transit region and goes downward or fly downward until reach a gap. And after that, it returns back to building state and starts building a new map, which is represented by the blue dots here. And for the red dots, it's the trajectory of the map of the vehicle. And here it stops. And also here in the upper right figures, some real pictures for the environment. And in the lower figure here, it represents the height of the map. And in this region, it was the takeoff region. And after that, it starts building the map for map number 1. And when the vehicle didn't get a gap, it starts to go downward in order to find a new gap. And after find a new gap, it starts to build another map, which is map number 2 here. And after that, it starts to land. Here are some comparison for the memory consumption between different methods for the standard point cloud and voxel and elevation map and the proposed method. The size of the environment we used was 10 meter multiplied by 10 multiplied by 3. It's for the width and length and height. And the size of the cell for the voxel of the expansive grade was 10 centimeter cube. Okay, 10 multiplied by 10 multiplied by 10. And for the elevation map, it was 10 multiplied by 10 for the cell. For the memory consumption in bytes, for the standard point cloud, it was 773 kilobytes. And for the voxel, it was 2.6 megabyte, and it's huge. And for the elevation map, it's 86.8 kilo. And for the proposed method, it's 4.7 kilobyte. It is clear that the proposed method is very low compared with the other methods, such as standard point cloud and voxel and elevation map. And for the percentage of the reduction with respect to the proposed method, we reduced for the standard point cloud by 99.39%, and for the voxel 99.83%, and for the elevation map 94.7%. Actually, it was an idea in order to decrease the memory consumption, because for search and rescue operation, there are hazard situations and we can lose the map. So we have to find a way in order to use low-cost sensors in order to fit the memory for it, and also to navigate the vehicle inside and indoor in unknown environments for the search and rescue operation. And even if we lost the vehicle, it doesn't matter because it doesn't cost too much. So we have to build a low-cost map with its parameters for the low-cost embedded and low-cost sensors, so it can't afford the huge and massive 3D mapping. Actually, it was the idea for the proposed method. And thank you very much. And if there's any question, I'm ready.
Great, Haitham, thank you so much. We do have a couple of questions. The first question is, what is the method for gap detection?
For the laser scan range finder, it gathered the point cloud around it. And if there is no point cloud or no obstacles in front of the vehicle, and the detection range of the vehicle for the laser range scanner range finder, it's 6 meters. So if the vehicle doesn't detect any obstacle in front of it until 6 meters, it can move forward and make the current map and build the current map. But if it moves and there is an obstacle between this range, which is 6 meters, so the vehicle stops building map and goes upward and goes downward in order to find a new gap greater than the 6 meters for the detection range of the laser scanner range finder. Okay?
Okay, great, thank you. The next question is, if you had affordable chip scale navigation grade IMUs for your application, what would be the difference in performance? So in other words, a navigation grade IMU versus a consumer grade IMU.
Actually here, the basic or the main sensor here is the laser scanner range finder. We just use the inertial sensors for the leveling. Okay, and that's it. But the main sensor here is the laser scanner range finder in order to build the point cloud and make the maps by using scan matching process in order to build the map. But for the inertial, we use the inertial for leveling, just leveling, because for the quad, when it fly forwards, it makes a little pitch down. Okay, so it will get some point cloud different than the time before. And if it stopped, because the map can hover and stop in the air and hover and make another fly, there will be difference between the scan matching, the one in the last and the forward one. Okay, so the scan matching process we will face some problem in order to make a good scan matching. That's why we make the leveling, and we use the inertial sensor in order to make the leveling, and that's it. We didn't use the roll and pitch for the inertial in another mean. Okay, we use it just for the leveling.
Okay, great, thank you. The next question is, what is the 3D navigation accuracy of the MAV when indoors? And is it a real-time navigation solution?
Yeah, it's a real-time navigation solution. Actually, the navigation parameters is the position and velocity and the orientation. The orientation here is the roll and pitch and the yaw. So in order to localize itself, for the vehicle to localize itself inside a map or environment, it has to get a good navigation parameters. Why? SLAM needs to make simultaneously process at the same times. Build the map and localize itself inside this map simultaneously. The problem here, the vehicle fly inside a known environment. It doesn't know anything about the environment. It doesn't have an advanced map. It doesn't have a previous map for the environment. So the vehicle has to build a map. But the problem here, it doesn't know its location. That's why we use a SLAM, and this is SLAM. So the vehicle has to build a map and at the same time localize itself inside map. So if it estimates a bad parameters for the navigation, which is position and velocity and orientation, this will have a great effect or impact for building the map. There will be a problem for the scan process, okay, and build a good map. So the two processes are affecting or are coupled together. So in order to build a good map, the vehicle has to estimate a good navigation parameters. And also there is a problem for indoor environment. If the estimation is bad or the accuracy of the estimation is not good, the vehicle may be at a location or a position, okay, and the real position is beside this point, and we are inside indoor environment. So the vehicle can hit itself for a wall or any obstacle may be present in the environment. So the vehicle has to get or estimate a good or an accurate navigation parameters for the navigation itself and as well for the building a good map. Okay.
Okay, great. Thank you. Let's see. Our next question here says, how does the vehicle know its final destination, and is there interaction with an operator?
Actually, there is for this method, there is no action with the operator. There is no human intervention. Okay, it's autonomously. And for detecting that the mission is finished, it is programmed for if there is no new gaps, so it's halt or stop, it's stuck, there is no new gaps, it will stop and then fly backward and using the implemented trajectory to go backward, okay? However, if there is a new gap, it will start building a new map or slice for the environment, okay? And there is another point or another restriction, the batteries, because the batteries for the map or even the drones is a very critical point, because the battery cannot afford a flight more than about 30 minutes, maybe 30 minutes. So the method is configured with this restriction. If the building the map or in the navigating inside this environment takes more than 20 minutes, it should return, okay? Because there is a return path or return trajectory until goes outside. So if it reach a 20 minutes, it will stop the mission. Or if there is no gaps are detected, it will stop the mission. But if we find a new batteries can give us good endurance or can make more than this time, we can change this restriction inside the code. It depends on the battery. And for the gap, it depends on the environment itself. The environment will be the main issue here, okay?
Okay, thank you. A couple of questions on the environment in which this could operate. So for example, one question is, would this method work in a cave? You had mentioned tunnel inspection earlier. So would this method work in a cave? And then on top of that, how well would a laser scanner work in environments with smoke or water vapor?
For the cave, or regarding the cave, we used here the IRKF algorithm, okay? And by the way, we submitted this IRKF algorithm, and we made this a novel algorithm, by the way. And it has a good results compared with other methods. But for the cave, we will not use the IRKF algorithm because the IRKF algorithm depends on the features. And for the cave, we can find features. So we can use another method. For example, iterative closest point, ICP, okay? Because it depends on the point itself. It doesn't need any features. So if you are inside the cave, you can use the proper method for the environment, and you can just code this, and it is very easy to change or swap between algorithms or the methods you want to use for the cave. And Rick, what was the another question, please?
The other question involved water vapor or smoke and the laser sensor.
Actually, we didn't make any exercise, or we didn't study for the smoke, for the laser. It's problem for the laser. Actually, I don't have any idea about the laser can detect during the smoke or no. Any sensor has some defection. For example, the camera can detect inside any smoke and can see. It will be blind, completely blind. For the laser scanner, I don't know. We didn't make this problem, but it's a good question. We can make this experiment in order to stand for that. If the laser scanner can detect obstacle or detect some obstacles around it and make a point cloud, yeah, it's a good question. We can make this experiment.
Yeah, okay. Next question is, what are your thoughts on dealing with error sources like an IMU drift or like Windows, transparent materials for ranging?
Okay, for the IMU drift, we make updates by the position or the location of the vehicle itself. We estimate it from the IRKF algorithm, okay, as the GPS update, okay. The IMU is drift and the GPS make an update for the IMU, okay. Here we take the position update from the IRKF algorithm, and I will show you here a picture. Okay, here. The output here for the IRKF algorithm is the position of the vehicle, okay, which is denoted by PX and PY and theta. So we can use this position as an update for the IMU. Like the GPS, there is no difference. We need a position update for the IMU, okay? And what was the second question, Rick?
The second question was, how would a transparent material affect ranging, like a window?
Yeah, window is a problem for the laser scanner rangefinder because the laser cannot detect the glass or the window, okay? So it is easy to mount another sensor like sonar, ultrasound, okay? It can detect glass or window. In order to make obstacle avoidance, you can add this sensor, and that's it. But it will not add for the method. The method can use alone without this, but if there is a glass, you can add another sensor for this avoidance. Okay.
Okay, great. We have another question on gap detection. How did you decide to build map 2 from map 1? In other words, what is the trigger in the algorithm from map 1 to map 2?
The trigger here in the figure that there is no gap is detected by the method. Okay. As I told you before in the previous question, that there is an obstacle, okay, for here inside this rectangle, okay, inside the range of the detection of the laser scanner rangefinder, which is 6 meters. So here there is no new space, okay, in front of the vehicle in the range for 6 meters, and the only space is in the backward, which is the implemented trajectory, and the vehicle save its trajectory, and it's know that it comes from here. So it's an already visited area, okay? And the new one, which is in front of me, there is an obstacles, and there is no gap in the range of 6 meters. So at this point, the vehicle stop, okay? And then go to the transient state in order to find a new gap. During this transit state, the vehicle fly downward, maybe make some yaw, okay, in order or hope to find a new gap. And when there is a space more than 6 meters, which is the maximum detection range of the laser scanner rangefinder, it is a new gap. So it stops the transit region and then go to the building state and make map number 2, which is the new map or the new slice. In the same manner, it will make map number 3 or the 3rd slice, and so on.
Okay, great. And on that,
What was the second question? There was another question.
let's see, hold on one second. I was moving on to the next one. Let me just scroll down. I think that covers it. It said, well, what was the trigger in the algorithm from map 1 to map 2?
Yeah, fine. I told you.
Yeah. So another one on the different maps, does the system use a different reference keyframe for each map?
Can you repeat the question once more?
Does the system use a different reference keyframe for each map?
No. Actually, it's an algorithm. IRKF is an algorithm. Okay, it's an algorithm. So we use only one algorithm for the process of the map building and scan matching. We use only one algorithm, which is the IRKF. Okay, but if you will fly inside, for example, a cave, you use another method like iterative closest point. And if you will fly inside another environment, you can choose the best or the optimum method you can use, okay? But you will use only one. You can change the algorithm during the flight for building map number 1, and you will choose another method for building map number 2, okay? You will use only one.
Okay, great. And our final question is, being autonomous, how does it decide between different gaps? Inside a building, for example, it could go out an open window.
Okay, for detecting the gaps, okay, the MAV will fly, and if it detects more, for example, more than one gap, it will choose any one of them, okay? And you can code it for selecting maybe the middle or the right. It doesn't matter if there is more than one gaps at the same location, okay? For the open window, actually and this will be the only gap. The MAV cannot detect an open window because the MAV doesn't know that it's a window, okay? And it will go outside. But this means that there was no any other gaps except this. So it finished the environment and it doesn't need to go any place because it was the only gap. That's why it goes through it.
Okay, great. Well, Haitham, thank you so much for your time and for this great presentation. We appreciate it. If you have not, you can download the full technical paper on our website at ion.org. You just need to if you have not, you can create a free account, sign in, and you'll be able to access the full technical paper. And again, the slides from today's presentation, as well as the recording of this presentation, will be available on our website tomorrow at ion.org. And we encourage you to come back, and something you can share with colleagues as needed. And again, Haitham, thank you for your time. We wish you a good evening. I guess it's dinner time over there. So thank you very much.
Thank you very much. And you have my email. And if there's any question, it's welcome to send me. Anyone can send to me if there's any question. And thank you very much.
Great. Thank you so much. Have a great evening. Bye-bye.
Thank you. Bye.